Hi everyone, this is my project on tuning active matter properties using differentiable programming. My name is Angela Situ and my supervisor was Dr. Megan Engel. So for some background information, what is active matter? Active matter is any micro or macroscopic system with internal source of energy, meaning it can move around. And so this can mean a bacteria colony, a bird flocks, or even a group of humans at a high enough density. And so why is active matter important and why do we care about it? And so actually, we see many different biological systems display properties of active matter. And so in this case, we have starfish embryos spontaneously assemble. And so if we're able to simulate active matter, we can then apply this to different biological settings and be able to understand many different processes. And so another property of active matter is that it can display something called motility-induced phase separation, or MIPS. And this is the spontaneous aggregation of active matter into a semi-solid state, or quite simply, it clusters. MIPS will occur as specific parameters. And for my research, I'll be exploring density and self-propulsion. So active matter will go through three forms. The first one is gaseous form, or free form, and then it'll begin to cluster or show MIPS. And then at high enough densities, will actually crystallize. And we can see the different crystal lattices here. The goal of the simulation is to create a new way to study active matter. And so we build a simulation based off of pre-existing code, and we will confirm it using literature values. And so we will be able to observe phase transitions from it and find maximal values at the phase transition. The method I used is called molecular dynamics. What molecular dynamics is that we are able to compute a force, and when we do so, we'll actually update the particle positions, and so we will see them moving. And we will integrate Newton's law of motions into it as well. And so the two parameters, density and self-propulsion, are manipulated using these two lines of code over here. And so how do we know when MIPS is occurring? We need to implement several different analytical measurements in order to conclude this. And so the first way is to use subvolumes. And so we will divide the simulation into grids. And this is important because, for example, in freeform, we'll have particles roughly in each square. But then as we have clustering occurring, we have areas of no particles and areas with a high number of particles. And then in crystallization, we have approximately an equal number of particles in each subvolume. And so with standard deviation, we will be able to take the standard deviation of the density of each subvolume. And over a range, we'll actually see a peak in the critical value. And so we will be able to see this in 1D histograms. When we take the average density of each simulation and plot them out like this, we can see that as we increase density, we have two peaks emerge, which is indicating that phase separation is occurring. And very clearly in this example, we have clustering happening, and corresponding to this, we'll actually see two peaks. And so when phase separation occurs, two peaks will emerge in our 1D histograms. And as we increase the density, as I mentioned, we'll be able to see clustering occur. And this is the same case with self-propulsion. As we begin to increase the speed of active matter, we will be able to see them clustering more clearly. And in this case of simulating it at 20, 40, and 80. And these are more results. This is active matter at a low density, which is still kind of in free form. And then at medium density, when it clearly begins to cluster, and then at high density, when we see crystallization happen. And so the conclusion from this is that we are able to build a new method that can be verified. And with this new method, we can also see the phase transition occurring. And so the next steps is to be able to find the critical values with other parameters, such as mass and particle radius. These are my references. Acknowledgements to my supervisor, Dr. Megan Engel, Trevor and Ella for their advice. And this project was funded by NSERC. Thank you.